think I got it. All right, let's start working at it. Last time we talked a lot about mirrors. And today's topic is lenses. Yeah? Yeah. Lenses. And then Wednesday we're going to get into, I think we get into applications. We look at how cameras work, telescopes, how the eyeball works. What else? Glasses, all that stuff. Glasses. Oh. All right. But before we really get into lenses, we got to explore a little bit more about refraction and how images can be formed through refraction. Because, when we're looking at lenses, light is passing through glass. There's a refraction that's going to take place. And actually the way we think about lenses is we treat them as two refractions, right? There's a refraction that occurs when you go from air to glass and then glass to air. So what we want to do first is deal with one of those, right? So what you see right here is considering what happens, how our image is formed when we go from, one index refraction to another one, okay? And we did a little bit of this before, actually. We looked at plane mirrors. And, no, we didn't. Well, we did. What was it? We looked at a plane surface, right? And how images are formed on a plane surface. That's right. Something's bugging me about our schedule. Let me double check our webpage here. Something doesn't feel right. Because I'm thinking about all the topics we got to do. And we're gonna have so much to cover on Wednesday. I mean, I'm on track here. Just seems strange. I'm gonna cover all that stuff on Wednesday. What? Apparently I do. So that's going to be an interesting day. Great. There's a lot to cover that day. I don't know, man. That's kind of nuts. All right, anyway. Okay, so let's talk about this one. So we're going from, in this particular case here, we're going from a lower index refraction into a higher index refraction. And so our light's going to refract, and we want to imagine what our image is going to look like here. Now, we're going to derive a very similar equation to what we did before with a little alteration here. So let's write down what we know about this setup here, because here's what's going on. We got our object here on the optical axis, so we're assuming here we have a spherical surface, like we do when we talk about our mirrors. And what's going to happen is this one particular light ray that we're looking at, it's going to hit the boundary there. We have an incident angle, which we're calling theta 1. I will let you know that, unfortunately, I've mixed up my notation a little bit in this lecture, so theta 1 and theta A are the same thing, and theta 2 and theta B are the same thing. I'm sorry I mixed up things there, but I did. All right, so the light enters the surface, it refracts, it closes up a bit. We get to theta 2, which is a refracted angle, and then the light comes down to this point here. So our image is being formed right here, and we can see we have the following relationships here. So if you add up alpha, let's try that again. You add up alpha and phi, you get theta 1. Okay, you have this angle here. Theta 1 is the supplement of the third angle. Therefore, the sum is equal to theta 1. We also have theta 2. So if you look at this other triangle over here, this triangle is not really labeled here, but the really huge obtuse triangle here, we have beta plus theta 2 equals phi, because again, same idea here. You have your two angles, and then the supplement has to add up to 180, but that's what phi is. And then we also have our law of refraction. I'm getting better at this. I'm getting better. What else is going on here? Let me think about this. Well, you got a bunch of tangents here. So if you notice, this length t here, which is where the refraction's taken place, that's involved in alpha, beta, and phi, right? So the tangent of, say, alpha is going to be t over s. The tangent of beta is t over s prime. And the tangent of phi is equal to what? T over r. Yeah. And then remember what we do here is we make a small angle approximation to help ourselves out here. So we're assuming that we're not right up on these surfaces. So when we do that, our spherical surface, we have this little delta here. That's what we called it before, right here. We got a little kind of delta going on here. Okay, don't do that. Why is it doing that? Be nice. Okay, right there. So in the limit that we have small angles here, and we have some simplifications. N1, theta 1, N2, theta 2. All tangents and all sines, because of the small angle approximation, just becomes their angle measures. So you can say here that alpha is, well, this is basically approximately alpha, and this is approximately beta, and this is approximately phi. And you got to do some algebraic gymnastics here. You can use the index of refraction equation here to eliminate your the theta 1 or theta 2, and then combine the alpha, beta, and phi together. And when you get through all of those algebraic gymnastics, which I'm not going to go through because it'll take me like 10 minutes to get through it all, and I believe the book most likely has got to derive it for you. It's pretty standard derivation stuff. We get to the following relationship. Now, this looks a lot like the mirror equation we had last lecture, with one big difference. The indexes, or I should say the indices of refraction, play an important role here. It's how we translate between the boundary of the two things. So the equation is very familiar, okay? Except here we have N1 and N2 paired up with S and S prime. So N1 refers to the object. So that's paired up with S. And N2 is paired up with S prime. S prime is our image here. We have a difference that's being done here. Okay, so again, you got to remember here that your N2 is what you're going into, N1 is where you come from, and that's our equation there. And we have special conventions for refraction. Okay, I mentioned this in the last class, that when you have mirrors, there's a certain convention for the signs of things, and it's different if you have lenses or other stuff like that. Well, there's a little difference here. In this case here, convex toward the object is going to give you a positive value for R. Concave towards the object is going to be negative. That was flipped from before. Okay, our convex surface is our positive here. When S prime is positive, the object is a real image. That means light actually reaches that area, and it's on the opposite side of the object. Okay, so the object's on one side and the image is on the other side. And if it's negative, it's a virtual image. That's always true, by the way. If you every time you get a negative for these S prime stuff, it's always a virtual image. And it will be located on the same side of the object. It will appear as if the light comes from that area, but it doesn't actually come from that area. So this is the equation that we're going to be working with when it comes to refractive surfaces. Okay, refractive surfaces. So very important to keep all these conventions in mind. It's very easy to forget them, okay, or to mix them up, you know. All right, so we saw this previously. You could take that equation and you could approximate it for when you have a surface that is basically flat. And that would mean that the radius of curvature of the refractive surface is effectively infinite. So the right side of that equation you just saw would come out to 0. And then when you solve for S prime, as you can see here, you're going to end up with this nice ratio of NB, right? So NB, just put over there. Yeah, NB over NA. Well, again, NA equals S. Is that right? I think I mixed that up. Can I write this down somewhere? Okay. So in this case here, when you're looking at an object under the water, you're going from the air, well, the light's going from the water to the air, so this ratio here is less than 1. And what that tells you is that your image is going to appear closer to, it's going to appear closer to you than how it actually is. And this dashed line that you see down here represents the direction it appears to come from. It appears to come from. Of course, if you go the other way around, it's going to look like it's farther away from you. That was, again, subject matter of a couple lectures ago, I believe. Okay, so we derived this. Oh, there's a negative sign here, right? That negative sign indicates that it's that's the same side, right? Same side as our object here. So that's supposed to be a negative. All right. So we kind of just said this before. We didn't really derive it, but this is where it ultimately comes from. All right. So anytime you have a plane surface, this applies. Okay. And because the well, I'll wait to say that, I guess. Let's keep moving on. All right, let's just jump right into a problem here. So the idea is that we have an object, say it's in a spherical fishbowl. We are going to assume that the bowl is extremely thin, so we don't have any major refraction happening through the glass. If there's a certain amount of thickness, it would offset things slightly. It actually creates a huge headache of a problem if we consider that thickness in there, but the thinness of the glass, the thinner it is, the more we can ignore it. But it's very obnoxious because you'd have to do, you know, an extra problem. You have to go from water to glass, then glass to air, as opposed to just going from water directly to the air. So the deviation would be a little bit different here, but not much different. Okay. All right, so the idea here is that when we go from the higher to the lower index of refraction, the light's going to open up more, right? Because you're going to lower index of refraction. So when it opens up more, if you trace things back, it's going to give the appearance that the fish is much closer to you. If you've ever had that experience, you've been to an aquarium, or if you've actually seen, you know, a personal aquarium, things appear closer to you, and it's this principle here. So now, we got to be very clear about our conventions here. So let's go through this very carefully. Let me go to my example here. Okay. So in this example, we're going from a higher index of refraction to a lower one. So N1 is paired up with S, okay? And because we're considering where our object is located. and N2 is where we sort of expect the image to be, but as you can see in the demonstration here, we should end up with a negative value for S prime. And that means it's a virtual image on the same side. Now, notice my radius of curvature. It's a negative 25 centimeters. Okay? Concave toward the object is going to be a negative radius because it's on the same side as our object. Anything that's on the same side as the object, when we're considering like the images, the radius of curvature, those are negative. Okay, so I have my equation N1S over S plus N2 over S prime equals the difference between them over R. So make sure you pair up the N1, whatever N1 is whatever is with the object. So N1 in this context is 1.33. The value for S is 10. We've got to look for S prime, but for N2 I'm going to put in 1. And then N2 minus N1, well, it's going to be 1 minus a 1.33, which gives me a negative value here. Okay, so if I write it down here, here's how it's going to look. We got our 1 point. We got to do my annotations, looks like. Click that. All right. Try that one more time. Okay, so we got 1.33 over what? 10? 10. Yeah. Plus 1 over S prime equals 1 minus 1.33 over a negative 25. So the top's going to be negative, the bottom's going to be negative, but when you move this thing over to the side here, this is going to end up being a larger quantity, the 1.33 over 10, and you'll be subtracting it here, and you end up with the S prime value being a negative 0.83 centimeters. So that means this object is going to appear on the same side. And so if you're a person in the air there looking at the fish, you would say that it's on the other side of the glass, and it's actually a little bit closer. I mean, you don't know that because you can't see where exactly in the glass is, but you know physics now, so you know it actually is closer than it really is. It says 8.3 centimeters. Right? It is a virtual image because it's negative. Okay, so this problem here, there's two things that stood out about this. Well, two things to be mindful of. Make sure you pair up the indices of refraction appropriately, and make sure you have the right sign conventions for things. R is negative in this case. Okay. Fantastic. Let's keep chugging along. Let's keep going. Bam. Wow, we got another one right off the bat here. Oh, let's look at this. We are now going from air to some type of glass here, right? And when we enter from the air to the glass, we're going to have an index of refraction here. We're going to have the rays are going to close up a bit, and because of that, it's going to give the appearance that this object is well, let's see here. We are looking. Oh no, we're looking at P here. Okay, we're looking at P. So the light comes from P, and we're seeing how the object is formed at P prime here. Okay. Let's just get into it and start defining the conventions here. All right. So when we do this, we are convex toward the object. Our object's at P. The surface opens up away. That's convex towards. So we have a positive 2 centimeters here. N1 is going to be the air, 1, and N2 is going to be the glass, 1.50. The object distance is at 8 centimeters. So we have everything that we need here. Okay, so the N1 over S1, the N1 is going to be 1 over 8. For N2, 1.25. We're looking for S prime. We have the difference here. This is going to be 1.52 minus 1. That's all divided by 2. You solve this equation, and we end up with 11.3 centimeters. It is a real image. Okay, the object is going to appear on the opposite side from the object, and it's a real image, and it's the opposite side. So that makes sense. Now, we have a relationship for our magnification. Okay? So this is different too from doing things with mirrors. And what's different is that the magnification needs to take into account the indexes of refraction. And the way we did this before is, in order to figure out magnification, we saw that there were similar triangles that compared heights of things to their distances. Well, that still applies, except now there's two different indexes of refraction. And so we end up with this new relationship here where we still do a ratio of the image to the object distance, but we also multiply them by these indexes of refraction. So in fact, what's happening here is this S down here, it's like you have this first term here, the N1 over S, okay? But then when you divide by that, you end up having, well, you have the N1 over S here, but then over here, if you divide by that here, the N2 is on the bottom and the S prime comes up top here. So it's kind of like you're taking a ratio of these two quantities here, all right? Anyway, let's put our numbers in here. N1 is 1. We have our image distance is 11.3. We have a glass at 1.52, and then we have our object distance. So this ends up becoming a minus 0.93. So that means when we see the object, it's going to be a little tiny bit smaller than it actually is, and it will be flipped. It will be flipped, and so that's what the numbers tell us. So far, there are two equations that we need to be mindful of here, and you need to make sure you take into account the proper sign conventions. We got a new equation for our magnification. Okay, it involves N1 and N2s. Okay, well, let's see here. If we have our, by the way, if we have Y's in here, the magnification is just equal to the ratio of the heights. Okay, the image distance and object distance are altered by the n's here, but not the y's. Okay. All right. Because like if we, if I mean, because think about it like this: if I told you that the object was like 10 centimeters tall, well, if it's smaller by 0.93, well, it's smaller by 0.93. The indexes of refraction taken into account here. They got to be taken into account at some point. We usually do it when we get our object and image distances here, actually. Okay. Hey there. Well, we got an in-class activity right off the bat here, but it's not like we're going to take a break because we've only been at this for half an hour, so I'm just going to go ahead and jump right into the problem here. Let's see what's going on here, though. This problem is different in one respect. We're not going from air to glass. We're going from water to glass. So everything else about the problem that we do is going to be identical. Everything is the same, okay? And you're only going to change your N1. That's it. That's really it. So let's look at it. So now I drew a picture down here to see what that's going to look like. Now, even though we've changed one thing here, we just said we're going to have water now instead, we now end up with a really different scenario here, actually. Now we end up with a virtual image. So N1 is the water, okay, down here. N2 is the 1.52. R is still 2. Image distance is still 8. But here's the thing. When we had air, there was enough refraction that the light rays started to converge. And that's good, because when they converge, they're going to form an image, a real image. But these rays that are initially divergent away, they hit the surface with glass, and there's not enough difference between the indexes of refraction now. What will happen is the light rays will bend, but they don't converge. they actually will continue to diverge, which means we're not going to form an image on the right-hand side. Instead, we can trace back those rays as they enter into the glass. And we see that our image is formed way in the back here. Okay. That's a big difference here. And, you know, it's not something you would see just by looking at the problem here. I mean, you see, oh, index of refraction is different. You don't think you're going to have a completely different scenario here. This is very different. But the mathematics doesn't lie here. So that's the thing. And 1 is 1.33 and 2 is 1.52. We have our same object distance. We have the same radius. You solve that equation, we end up with a negative 21.3. That's a virtual image. And in the convention of refraction, that means we're on the same side. Okay, I drew the picture out because it's good to see why. I mean, when you enter into this, you know, even though we're going from lower to higher, the light rays are going to bend for sure. The question really is, you know, do they bend, you know, enough? And there's a balance point here. At some point, you could reach the focal length of this thing, right? And then when you do that, what happens is these light rays go parallel. Okay, and if you you know, if you get them to bend anymore, either by changing the index of refraction, for example, all of a sudden it's conversion, or if you bring it closer, it'll diverge. So anyway, that's what's happening here. Let's do our magnification now. Same equation we had before. That negative sign is going to cancel this negative sign, and we're going to end up with an image that's actually larger and upright or erect. And so if this is, you know, whatever kind of object is here, if it's a balloon, you know, you're going to have a balloon that looks 2.3 times larger, which is 2.3 times more happiness, because balloons are filled with happiness and they deliver happiness. So, unless they're mylar balloons, then they can start fires and burn houses down. Those are different. Don't ever buy those. Anyway, so, the mylar is what it's called? I think it's what it's called. Anyway. Okay, now, there's some consistency you noticed here. There's only 2 equations so far. And the most challenging thing about this is to keep track of the conventions for things. Now, what's nice to do, when I do these examples, is as I try to do a 2-scale image. Because if you do a 2-scale image, it puts a picture behind things. I mean, at least when I studied physics, when I was going through things, I always had pictures. That was just the way I did things. I always had to see a picture of things. And so, just more than anything, I want to I want to verify that my numbers make some sense. I mean, mathematically, I can go through this, you know, until I fall asleep tonight, and just read over all the numbers repeatedly. But until I see a picture, not really quite satisfied. So, of course, that takes a lot more time and patience. And if you have either of those 2 things, well, I recommend you do a lot of pictures. But we only got so many hours in a day. All right. Any questions about this stuff so far? I mean, I think it's pretty straightforward, but I don't know. Let's jump into lenses. Sort of. We're ready to jump into lenses because we've already dealt with refraction things. And lenses are simply that. They're refraction. And there happen to be refraction at 2 different surfaces. But there's a easier way to do things and a more complicated way to do things. We're going to start with the easier stuff and then work our way up. And by the time we get to the lecture on Wednesday, we'll get up to the harder things. But the most important aspect of when we do our lenses is that we are using what we call a thin lens approximation. And what the thin lens is, it's sort of similar to a lot of the other approximations we have, is that if we consider our object and image distances, the thickness of the lens is small enough that we don't need to consider it. Now, maybe you say, well, maybe I want to consider it. Maybe I do. Well, okay, we'll wait till Wednesday. Because on Wednesday, we say, okay, let's not consider we have a thin lens. How does that actually change things? And then what we do is we combine two lens equations. Because what happens is, check this out. This is wild, right? We have our object to the left here. It comes through, and we're going to make this thin lens approximation. The light just goes through, it's focused down, and an image is created. But here's the reality of it. Ready? Put a helmet on here. It's going to blow your mind. When you have your first surface on the left-hand side, you have an object, and then that surface on the left-hand side creates an image. That image becomes the object for the other surface. And then you have a second equation that you do that helps you figure out what that image is going to be. And that's what's really going on behind the scenes here, is that you're doing the problems we just did at the beginning of the lecture. You have an object that forms an image, then that image becomes the object for the second surface, then you have an image there. Okay, for the thin lens approximation, we cut out the middleman there and say, well, we don't have to worry about that because those are going to be they're not going to be very different from each other. But on Wednesday, it won't be that way. We're gonna say, you know what, it's not that bad. Let's do it, and then we'll do it. All right. Now, there's two types of lenses we're going to work with here: convergent and divergent lenses. And you can see them by their shapes. You can also see them by their behavior. Okay. The one on the left is referred to as a convergent lens. It's the kind of traditional lens that you're used to seeing. And what happens is they make the light come to a focus, and they create an image on the opposite side, okay, on the optical axis there. Whereas a divergent lens makes the light diverge away. And so no images get formed on the right-hand side. Instead, you have to trace back, and you create virtual images that are on the same side as the object. That's it. That's the difference between the two. All right, let's start digging into this. We're going to deal with convergent lenses first, and then we'll look at how the divergent lenses go. All right. So, like I said, we are going to run under the assumption here that our lens is sufficiently thin, so that we're really only considering the light being refracted one time through here. As you can sort of see in the picture here, we kind of assume everything just happens right on the midpoint here. Anyway, now what's interesting about lenses, though, is that light can go either way. It's not like a mirror. And so we actually have two focal lengths, but they're the same distance on either side. So in this case here, if you have parallel light rays coming through, they're going to converge down to a point at the focal length that's on the right-hand side. And that's it. And if we have the opposite taking place, what if the light comes from the focal point on this side and exits out where it's going to run parallel? So, lenses work both ways. Therefore, you can speak of there being a focal length for both. But guess what it really is? It's the focal length for one surface and the focal length for a second surface. That's why there's two ultimately, because there is two surfaces here. Okay. All right, so notice the equation at the bottom looks pretty darn familiar. Yeah? It's the same equation for a mirror. You say, well, these aren't mirrors. This is, that's reflection. This is refraction. Well, it does just happen to turn out that way, actually. If you look here, you can see some relationships. So I'm not going to fully derive this thing, but I will point out some interesting aspects to this. There are a bunch of similar triangles here, right? So one of your similar triangles is this, that's formed from the object. Oh, not really good at the triangle. But that, which is dictated by alpha here, is the same as this other triangle here. That goes down here. Boy, I can't draw straight lines. So those are similar triangles. And then when you consider what's happening at the focal length, you got this triangle up here, and you got the other one with beta. And that allows for some really interesting relationships between things. And we do end up with, I'm going to clear this out because it looks like my 4-year-old drew it, so I'm gonna pretend that it's not there anymore. No, I can't do it because I annotated my PowerPoints. Anyway, so anyway, when you look at the relationship between those, because like this over here, this is your y over s. This triangle over here is your y prime over your ys, and you can relate all the angles here, and you end up with a very similar, very similar relationship here. What are the conventions? Well, they work similar to the refractive surfaces. So if S prime, is that my next slide? Because I don't want to ruin it. I think it's my next slide. No, it's not. Is it one of my slides? I don't know. Maybe. Maybe no. I don't want to step on my own toes here. No. Why did I do that? I don't know. Anyway, S prime, if it's positive, that means the image is on the other side compared to the object, and it's a real image. If it's negative, it's a virtual image, same side as the object. Okay. Here, your focal lengths are always positive. Why? Because you always have convex toward your object. The nature of the convergent lens is convex towards the object. We already called that positive, stays positive here. So that's why I don't do it. The conventions are the same from what we did earlier to what we're doing now. So that's nice. That's very nice. Anyway, the unfortunate thing about this equation is it is the same for mirrors, but there's different sign conventions for mirrors. So it's very easy to get mixed up with all that stuff. So really keep that in mind. You know what you're dealing with here. My advice to you is to not mess it up. That's my advice to you. It's good advice too. Don't mess it up. How do you not mess it up? Well, you just study and you do all your work and you pray. Do a lot of praying. And then maybe it works out for you. Okay. This stuff's nice. I hated this when I was in college. I hated optics. Hated it. Which is weird because then I became an astronomer, which makes no sense, but whatever. All right. Anyway, let's move on here. Let's look at some examples. All right. So we have image formations with lenses that are very important here. So we want to go over the conventions for that as well. By the way, you can certainly do this for the refractive surfaces like we did before. I just happened to not do that one, but you certainly can. In fact, it follows the same thing as you see here. We have 3 principal rays here. 3. One, the first one is like the other first one. It's a parallel ray to the optical axis, hits the lens, goes through the focal length because it was a parallel ray, and then moves on. Ray number 3 is very similar to ray number 2, where you first go through the focal length, then you run parallel. Okay. Number 2 is very similar to number 4, where you hit the optical axis. Now, because this is a thin lens, what happens is, if this is sufficiently thin, then when the light passes through the center of the lens, the deflection, because what would happen is it would get slightly deflected. Okay, so it enters through here, and what it does, it actually would shift the ray up. It possibly would shift the ray up just slightly. But we're considering that our rays are thin, so that when the light goes through there, it effectively does not deviate at all. So what you do is you simply draw a straight line that goes from the top of your object through the center of the lens. So anyway, these are very easy to draw. Parallel lines, you connect from the axis of the lens to the vertical axis here, to the focal lengths, and you have one that goes right through the middle there. 3 rays, not 4, 3. We don't have a 4th ray because the other one involves the radius of curvature, which I suppose you could do here. But we don't really think in that manner. It's not helpful to think, because when you start thinking about the radius of curvature, then you really have to start thinking about the fact that the surfaces are actually different things, which again, wait till Wednesday for that stuff. It's not particularly hard or anything, it's just a thing, you know. So let's do a similar thing to what we did the last lecture. Let's sort of explore the different possibilities that we can have here. So we have our lens here, Convergent, and it's going to be a focal length 20 centimeters. So what we want to do is you want to put a an object at a distance that's far out from the focal length. We want to put one that's at the focal length. We want to go within the focal length, and then get this. This is wild. We're going to choose an object that is on the other side of the lens. I know this is weird, but negative 40 centimeters is our S value. You say, Professor McGovern, that doesn't make any sense. And to that I say, sort of. Okay? Why? This is strange. Why do we have... Why is this? Because what I mentioned before is this principle of, if you have two surfaces, and when you look at the details of this stuff, the first surface creates an image that becomes the object for the second surface, and it's very possible in a lot of situations that the image that's formed through the first surface becomes a virtual image for the second surface. Right? That can happen. So I'm going to look into that possibility. It doesn't make sense if you have like a single surface, but it makes sense if you are dealing with, you know, a more realistic situation, which you will see later on. Again, I keep saying that. Maybe on Wednesday I don't. Maybe on Wednesday I just talk about a totally different subject. Maybe. Maybe we talk about, what do you want to talk about? Let's talk about superconductors. That'd be fun. Superconductors is pretty cool. Solid state, cold physics. Ooh, cold physics is fun. It's not fun at all, actually. It's pretty much a nightmare. All right, let's get into the examples here. Cold stuff. Oh man, look at these. These are beautiful. My handwriting's decent. All right, for once. All right, so let's do this. We have our lens equation here. We have our object distances. We're going to start with the one at 50 centimeters. Our focal length is 20. It's positive because we have a convergent lens. That's it. I solve the equation, and I get a real image at 33.3 centimeters. Positive 33.3 centimeters. Check this out. We were out beyond the focal length. The image that's formed is also out beyond the focal length. However, the nature of this equation here, if I take my object and I slide it back, it's going to cause this image to slide to the left. Because the farther I get back, the closer I get to infinity, which means the image gets closer to the focal length. Isn't that cool? It is. So now we're going to throw in for our magnification here. For lenses, it's the standard magnification, S prime over S. Because ultimately we're considering, because you say, well, what's the index of refraction? That's when we go from higher to lower, but here we're effectively going from same to same, air to air. That's why there's just the S prime and S here. Minus 2/3. So it is shorter and it's flipped. And that's standard stuff there, standard stuff. If we place our object at the focal length, well, you know what's going to happen there. If the object's at the focal length, when it goes to the lens, the rays are going to run parallel, and the image is formed at infinity. You don't have an image. You don't have an image. It's at infinity. If you try to look at this thing, you know, it's just going to look blurry, distorted, and weird. Okay. All right. If we are within our focal length, well, now we have this situation, and let me zoom in a bit so you can see how this works here. Look at this. I'm within my focal length. So what happens? Let's do ray 1. It goes parallel. Then it comes through focal length. Great. What about ray 2, the one that cuts right through the optical axis? Okay, I draw that one. Uh-oh, what's happening here? These are not convergent. They're divergent. Okay? Now, 3 would be a little bit, weird to do here. You'd have to kind of trace backwards here, right? And then you come up and then you run parallel. So anyway, everything diverges here, right? You have to trace back, run up, hit your lens, and then it goes parallel. So the other ray will look like this, just if you want to know, if you're curious. Okay, it would look like this. It doesn't even work. Imagine the lens was bigger though. Yeah, that's why I didn't draw it. Because it looked like that. Anyway, everything diverges. So that means where's the image? It's on the other side because you trace back to get to your virtual image. So when we do the equation, uh-oh. It doesn't matter. Let me erase it then. So our value for S is 15, the focal length is 20, so we're less than the focal length. That means we're going to end up with our negative 60. So it's a virtual image. It means it's on the same side as the object. And what does this object look like? Well, because of the negatives here, it's going to be an upright image, and it's going to be a lot bigger. Guess what that's called, people? A magnifying glass. That's what a magnifying glass is. It's exactly what a magnifying glass is. And so you just put that thing up real close, and you get within the focal length, and it magnifies things. It gets really, really big. And you can see the way this works here, right? If you make, S really big here. No, actually S prime. You want S prime. If S prime is really big, right? And so you have to get closer and closer to the focal length. If you put things really close to the focal length, you end up with a huge value of S prime. It means you can really magnify things. So that's kind of cool. This is effectively your magnifying glass, which we'll do that in the applications next class. Okay, so here's the crazy thing about this, though, because guess what this virtual image can become an object for another lens. So that's kind of why we have this other example of the negative 40 here. So let's look at that one. Let's look at it. Here we go. All right, so this is weird. As I mentioned, and we zoom out just a touch here. So our object is over here. It's kind of hard to see. Let me annotate this so you can see us a little bit better. There we go. Look at that. So to do my ray tracing here, well, okay, I have to have a parallel ray. So I got to trace back here. And then we hit our lens, and we have to go through the focal length. So the light's actually doing something like this, like that. And then there's ray 2 that goes right through the middle. And ray 3, remember, it has to go through the focal length, then it runs parallel, which is this line right here. Anyway, on the left-hand side here, everything is divergent, so everything converges over here. It means the image is formed on this side, actually. So even though we have this weird virtual object, I mean, mathematically, everything works out. S is minus 40, focal length being 20. You solve for S prime, we get a 13.3. Positive. Okay? So why did I call that a virtual image? It's not a virtual image. This is not a virtual image. I forgot when I did the calculation, the 40 is negative here. So you do end up with a positive value. And that means Mr. Mark McGovern. Oh, wait, that's fine, actually. Never mind. That it's a real image, not a virtual image. It's real. That's the only thing that's different. Real. Because what happened, this is what's weird. The light rays, so the way we actually present this, which is actually an interesting perspective I didn't think about, but having a virtual image, a virtual object, is equivalent to saying that you have light rays, for whatever reason, come into the lens and they're convergent. Normally you have light coming into a lens that's divergent away, and then you focus it back down. Well, having a virtual object is like having your rays already start converging. And so then what happens is they converge faster, if you can say that, and they create a real image here. So that's the one thing I messed up, is this is not a virtual image, a real image. I'll have to update this when I post it, but it is smaller and erect and all that stuff's fine. Just the thing I forgot is when I did the equation, I didn't put in this negative here, and you do get it to be positive. It does come up positive, but when I was just punching my calculator before the break, it got to be a negative, and so I got confused. But anyway, okay. So questions. Let's go over these questions here. All right, so I got several questions. There aren't too many questions today, but I got a couple. So we have a lens creates an image as shown, as you could see here. We got a object and we have an image formed, and as you can see here, it looks a little bit bigger. So what do you think's going on here? What would cause this? What would do this? Based on what I just told you, you know. But the answer is A. Okay, why? Well, we went through the examples, right? If you're outside the focal length, you're creating a real image that's inverted. If you're on the focal length, no image. If you're within the focal length, you got a virtual image. So we got a real image here. We're large on the focal length. All right, now, same situation here. Okay. What's the image distance? What's that? Tell me what you think about that. A, same deal. So you're outside the focal length, you're outside the focal length. Now, the way it works here, though, is if you shift this object around, all right, if I go further out, this comes further in. If I push further in, it goes further out. It's you're toying back and forth between focal length distances here. But in both cases, we're bigger than it. Okay, last question before we jump into some other stuff here. It's B. Okay, get this. It's a real image. That means we're bigger than the focal length. Okay, so that means A is wrong. Now, how far can we go out here? Well, we're taller. We're taller than it, right? And so if we're taller, think about what magnification is, right? Magnification is S prime over S. So if S prime is bigger than S, and we have a bigger, taller, then we're actually within twice the focal length. Twice the focal length. If we were to put this thing really, really, really far away, right? What happens if you put it really far away? If you put it really far away, if S is much larger than S prime, you can see what happens to the magnification here, right? It approaches, approaches 0, really, right? If you make S super big, go ahead to S prime, and that's what happens when you push it back more. So if we have an object that's actually bigger, an image that's bigger than the object, then we're not that far out. So let's see, what's up with this 2F here, though, right? Let's go on with this 2F. Well, anybody remember what 2F is? What's that? There's another quantity we haven't been talking about here. Anybody remember where that is? Radius of curvature. You got it. And what happens when you put something in the radius of curvature? Do you remember from last time? If you put something in the radius of curvature, the magnification is 1. So if we're within 2F, or the radius of curvature, we got a bigger object. If we go beyond that, we got a smaller object. All right. It's a lot of things to keep in your brain, right? A lot of things to keep in your brain. A lot of stuff to remember. Okay, let's keep going with this. I think we're doing divergent now. No, we're not. Oh, we're doing the magnifying glass example. All right, so we are going to take another example where we place our object within the focal length. Okay, so as I mentioned here, you're creating a virtual image that gets real big, and that's what effectively a magnifying glass is. So we're over here, our eyeballs are over here, trying to see this thing here. And if you trace stuff out here, remember, You got to trace back to the focal length. You come up, you hit the lens, you run parallel. You got one that passes right through the center of the lens, so you got to trace back to see what happens there. And then your third one is you run parallel first, and then you go through the other focal length. You can see the rays diverge away, so that means the image is virtual, it's on the other side, over here. And so we got a much bigger object, right? And it's on the same side. So let's do the problem then. So, yeah, let's go to it. All right. So it's a convergent lens. The focal length is 6, positive 6. We hold, the magnifying glass 4 centimeters from the flower. That would be S. We solve for S prime using the equation, and we get a minus 12 centimeters. We have a virtual image. It's 3 times farther away than it actually is. Magnification is minus S prime over S. We get a value of 3. It's upright and also 3 times larger. And see what happens when you do this here. If you start to move this object closer to the focal length, well, I mean, if you're holding the magnifying glass, you're pulling it back more, right? You pull it back more, you're increasing the value of S here, and it starts to approach F. That means what happens is these two quantities start to get close to each other, and since you're taking the reciprocal, you can end up with a really big number here. And if you end up with a really big number here, you're going to end up with a really big number in the magnification. That's it. That's your magnifying glass right there. Fantabulous. All right, let's keep going. Stamp collector uses a magnifying lens that sits 2 centimeters above the stamp. Magnification is 4. What is the focal length of the lens? Very similar problem. We're within the focal length. Our object is right here. We do our rays. Again, we have a ray that comes up and goes straight across. Well, that's not ray 1, right? Ray 1 is this one right here. We go parallel first, right? And then we cross, no. Yeah, that was the first ray, right? We go parallel first, then we go through the focal length. Yeah, sorry, that's the first one. The second one is when you go through the center of the lens, and then the third one is when we go through the focal length on the left side, and then we run parallel. And again, they diverge away, so we trace back. We can see here our object should be way up here. That's the whole length of it. You can do the same thing for the bottom of it, and you end up down here. Okay, so if you draw the rays down here, well, let's just do it. Let's just do it as an example. So the first ray, if I do it on here, right, is going to, has to go through the focal length here. Well, I'll do the first ray. The first ray goes parallel, and then comes up like that. That's ray 1. Ray 2 goes right through the middle, but then we backtrack that. Well, actually, it should go down to there, right? This one backtracks down to here, and then the other one we have is focal length, right? Something like this. Looks kind of crazy, right? And then it goes parallel. And if you backtrack that one, I guess I didn't draw that correctly. That one wasn't drawn so nice. Let's try that again. Because you got to go from focal length to through the object, and I went a little too high on that. So now this is not a real ray, obviously, right? Because we're not hitting our lens here, but the image formation physics is still the same. It's like that. Like, I gotta make sure I hit the edge there. That's the edge. And then this goes forward. So I trace back, and I get a little lower. Not perfect, but anyway, that's how the rays would look there. I wish I could do dashed lines here. It's not so easy, though. All right, let's just do the numbers, though. Let's do the numbers. Clear the drawings. Clear the drawings, please. Okay. S is 2 centimeters. The magnification is at +4, which means we're going to have to use the magnification to figure out our image distance. Now, if it's magnification of 4, that means two things. That's how much farther away it is, and that's how much larger it is. So we're going to end up here with 8 centimeters for our distance, and it is going to be a negative value, so it is a virtual image, and it's way back here. So it's 4 times further away. It's going to appear 4 times larger. If I want to figure out my focal length, once I get the magnification, now I go to the lens equation and I solve for f, and we get a 2.7 centimeters. So we were close. You notice the magnification is bigger than the last example, right? So we'd have to be closer than we were in the other one, which we are. And good. So it's the same problem, right? We kind of went backwards, with it, basically. So good. All right, let's get to the divergent lenses and wrap this up for today. Divergent lenses, well, I sort of explained what those were already, but the light rays go out. So that means the image is going to be on the other side. When we have divergent lenses, these surfaces are concave toward the object, and the convention we talked about at the very beginning of the class is that means your focal length is negative. Divergent lenses, negative focal length. And guess what else is different? Nothing else is different. Nothing else is different. Just make sure you make your F's negative, and just tread lightly, because there's a lot of room for mistakes. The wrong negative sign somewhere. There's just a lot of equations and relationships. But that's really the only major difference we have here. Focal length here is negative. Fantastic. All right. So in both cases, right, if the rays are coming in parallel, they're going to diverge away, and they're going to come back to the focal length, or we take a convergent source of light and then runs parallel, which means they're all pointed basically at the focal length. So we create this nice parallel beam of light if we can predict how this is happening. All right. So for ray diagrams, not different, but it's that tricky back tracing thing. Our first ray is parallel to begin with. We hit the lens and we diverge away, but the idea is that we're supposed to hit that and go through the focal length. Well, that's going through the focal length back here, though, right? Because our rays are divergent. So what I would do to draw this is I would, let me just illustrate this the way I would do it. Where's a purple? Let's do a purple here. Let me get a good purple line in here. So I go through. That's a little too similar. And then you go through the focal length, okay? But that tells you how you backtrace that, so you continue forward to see what the diversion ray is going to be. All right, number 2, we go right through the optical axis. That's not different. That's the same. That's the same as the convergent lens. And then the other one is, well, we have to go through the focal length on the other side, but then what happens is we backtrace this as a parallel line when we get there. And then you can see how the emergent ray is going to look. Okay, so parallel through focal point, through the middle, through focal point, then parallel. And we can see we form an image here. We have our object up here. We have a virtual image here. We're a bit out from the focal length here, so you can see what's happening. It's kind of the opposite, right? It's kind of the opposite of the magnifying glass. Maybe. Let me think about that for a minute. Well, I guess this is sort of like, it's not though. It's going to say, what is like this? It's not I don't know. I was going to say like no, it's not like a telescope. It's not like a telescope at all. Well, I don't know. Correct your vision with, like, some people's vision's corrected with these kind of lenses. Something I could think of off the top of my head. I can't think of another example right now. All right, let's clear that out. All right, question for you here. So we got this convergent light. We're going to shove this divergent lens right in there. Right? That's the focal length right there, which, as you can see when we line this up, right? That's going to go right up there. Oh, that's a nice purple. It's like a lavender. I like that. That's a very nice purple. All right, what do you think's going to happen here? Where are we going to end up with if we shove that lens in there, you know? What's going to happen? If you said D, well, pat yourself on the back for me, because one, we're not in class, and two, I can't touch a student, so I would just air pat you on the back. Say good job for that. But yeah, the principle here is that the rays are coming in and they're reaching a convergent point that's here that matches the focal length. That's the definition of focal length. So we expect those rays to now run parallel. Okay. Fantastic. I think I got two more examples. I do. So in this example, we have a divergent lens. We have an object placed out far to the left here. We're going to create an image of this. And we want to determine what the magnification is. So, right, so how are we going to handle this? Well, everything that we've done for convergent is the same for divergent with one exception, and that exception is the focal length is negative. That's it. Let's jump into an example. This right here. All right. I don't know what kind of flower this is. I apologize for that. I didn't really think that far ahead. But let's see here. We have our object distance to be 100 centimeters. Great. We have our focal length as a -50, a divergent lens. We put it through our lens equation. We end up with a negative 33.3 centimeters. It's negative. That means virtual image. That means it's on the same side as our object. It is within the focal length as expected. Now we're going to go find out what the magnification is. It's the ratio of the image distance to the object distance. And the image distance is already negative. We already have a negative for the magnification. So we find that we have an object that is upright, and it is 1/3 the size. Now, what if we play with this? What if we push out the object farther and farther and farther away? What's going to happen? This image is going to start to creep closer and closer towards your focal length. And it will get smaller and smaller and smaller. Look at the magnification. If I push my object distance out very, 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 very far, S gets really big. That means this ratio gets really small. The magnification becomes very, very, very tiny. Okay. And so I suppose if you make this thing go out far enough, you could contain the entire universe right next to the focal length, I suppose. Or you could see it at least. Interesting. That's not true at all, of course. Anyway, so that's the only thing that was different about this, right? And having the negative here for that. But it's nice to play around these numbers. You know, like if I push this forward, what happens? If you push this forward, you know, this is going to get bigger and bigger. And then if you get, you know, within here, you got a totally different thing going on here now. Right? All right. Anyway, let's do one more example here. What are we doing on time? Oh, great on time. Let me think here. All right, I think we're good. Yeah, we're good. Let's do another one. What is going on here? Yeah. A lens forms an image of an object. That's nice. The object is 16 centimeters from the lens. Okay. Oh, we don't know what kind of lens it is, do we? We don't know what kind of lens it is. Oh, no. All right. The image is 12 centimeters from the lens on the same side as the object. Oh, maybe we do know. Maybe we do. So, this is good. We don't really know what we're jumping into here, so let's think about it. The object distance is a positive 16. The image distance, we're on the same side as the object? That's a virtual image. That's a negative 12. Positive 16, negative 12. Well, let's find out what our f value is. We're going to put it through the equation here. We end up with a negative 48 centimeters. We got a divergent lens. We got a divergent lens. That's how you know it comes out negative. So we're within the focal length here. So this is a weird thing, but I drew this out. Okay, so there's my object at 16 centimeters, and let's trace over these. Let's trace over these. With these rays with this beautiful lavender. I want to stick with the lavender for a little while because I'm digging it. I'm loving that color. Anyway, so we have our first ray that runs parallel. Okay. Then we have to sort of trace back to the focal length on this side, and we see that we have a ray that comes up like this, right? And then we want the one that goes right through the center of the lens here. So that's going to go straight down like that. Uh-oh, we got a divergent stuff going on here, right? And the other one's going to run through the focal length here like that, but then when it hits the lens, right, we're tracing back like this. So you see where the intersection is? The intersection is right there. Okay, so that means these things are on top of each other here practically. And so, well, let's work out the what are we trying to do here? Focal length, we got it. If the object is 8.5 millimeters tall, how tall is the image? Okay, well, we got to work on magnification then. So the magnification here is going to be minus s prime over s. It never changes. We end up with a upright image, as you can see here. This is upright. It's a little shorter. Apparently, it's 75% shorter, which does work out with our ray tracer here. That's nice to know. And then, of course, if it's 3/4 the height, which is 3/4 times 8.5, right? So that's going to be 6.4. It's a smaller object, for sure. Draw a pitch-pull ray diagram. I already did it. Now, if you got the time, do it. What you got to do if you want to draw these out to scale, you really want to have a what are those things called? Compasses, right? Compass. Those things that you had in school that you just used to stab your friends and you didn't really use them for what they were supposed to be used for. At least that's what I did. So what you do is you have a compass and you just set out an arbitrary length, right? So, if it's 48 centimeters, we'll pick something that's 48, but then everything else goes to scale. So if you pick this distance to be 48, well, then you measure up to scale, So say, for example, this is supposed to be 3 inches, right? You choose 1 inch over here. But if you draw out your surface to scale, right? Draw out the focal length, draw out your object distance, then do the ray tracing. And, after you do it a few times, it becomes clockwork. It's quick. You got to do ray tracing on your homeworks, and I will be asking you on the exam to do your ray tracing as well. We have a lot of examples, so you should see how that works. Okay, that is it.